Good day, I'm Marc Tabadero, and I'm here to present the concept of noise in electronic communications. So what is noise? It is any unwanted introduction of energy tending to interfere with the proper reception and reproduction of transmitted signals. It is also a random or undesirable electrical energy that enters the communication system by the communicating medium or channel and interferes with the transmitted message. So there are two categories of noise, namely correlated noise and uncorrelated noise. Correlated noise is a noise that is mutually related to the signal and cannot be present in a circuit unless there is a signal present. In short, it is directly proportionate to the signal present of a given circuit, thus, no signal present, no noise. Uncorrelated noise, on the other hand, is a noise that is present regardless of whether this signal is present or not. This noise can be divided into two types, namely, external noise and internal noise. So before that, I'd like to introduce first the concept of correlated noise. So one of the types of correlated noise is harmonic distortion. It is also known as the amplitude modulation distortion, which occurs when unwanted harmonics of a signal are produced through nonlinear amplification. So for example, we have a given pure sine wave and we have a distorted sine wave because of the unwanted harmonics that are produced through a certain nonlinear amplification. The second type of correlated noise is intermodulation distortion. It is a noise that generates unwanted sum and difference frequencies when two or more signals are amplified by a nonlinear device. So for in the given picture, we have the input frequency spectrum, which has an F1 and F2. When we create the output frequency spectrum, we have a spectrum that contains an unwanted sum and unwanted different frequency by a nonlinear device. Therefore, this type of noise is an intermodulation distortion. So for the uncorrelated noise, we have basically mentioned these two, which are external and internal noise. So what is the difference between the two? External noise is a type of noise that affects the communication system coming from the outside environment, such as atmosphere or even space. Internal noise, on the other hand, it is an electrical interference generated within a device, such as transistors, operational amplifiers, and diodes, or even circuits such as amplifiers. So it is divided into types of noise, external and internal noises. Namely, for the external noises, we have the atmospheric noise, the extraterrestrial noise, and industrial noise. Internal, on the other hand, it has an excess noise, the avalanche noise, the burst noise, the shot noise, and the most famous, the thermal noise. So we'll proceed first on the external noise, which is the atmospheric noise. It is also known as the static noise, which is a naturally occurring electrical disturbance that originates within Earth's atmosphere. It is usually caused by lightning discharges in thunderstorms and other natural electrical disturbances occurring in the atmosphere. This noise has a very high peak to average power ratio that usually dominates at lower frequencies. The second one that we need to consider is the extraterrestrial noise, or also known as space or deep space noise, which consists of electrical signals that originate from the Earth's atmosphere. So it is divided into two, namely solar noise and cosmic noise. Solar noise is an electrical disturbance that generated directly from the sun's heat or the occurrence of a solar cycle activities such as corona and sunspots. Cosmic noise, on the other hand, it is also known as a stellar noise that was radiated by a distant star. It is also continuously distributed throughout the galaxy. So, and the final external noise, which is industrial noise, or also known as man-made noise, that is usually produced by mankind. It is impulsive in nature and contains a wide range of frequencies that are propagated through space in the same manner as radio waves. Also, it is more intense noise in the more densely populated metropolitan and even industrial areas. The sources of the industrial noise are the following: automobile and aircraft ignition, electric motors and switching equipment, leakage from high voltage lines, and fluorescent lamps. Now we have discussed about the external noises, we will now proceed to the internal noise. So the first type of the internal noise is excess noise. It is also known as the modulation noise, or 1 over F noise, or just simply pink noise, because noise power varies inversely with frequency, as I mentioned before, 1 over F, but it is proportionally more energy at the low frequency end of the spectrum. It is usually used for testing and setting audio systems in our amplifiers or even speakers. The second internal noise that we need to consider is the avalanche noise. These are the large noise spikes, that as you can see in this figure, that are present in the avalanche current due to oscillation that result in the avalanching region. So we have a distortion right here that created a large noise spikes that is present in the avalanche current due to the oscillation. Next, we have burst noise, or is also known as the popcorn noise, which is a low frequency noise found in usually transistors, which appears a series of bursts at 2 or more levels. The next one is shot noise. It is usually caused by a random arrival of carriers, mainly holes and electrons, at the output element of an electronic device. It is also due to random variation in the current flow, most specifically in active devices such as tubes, transistors, and semiconductor diodes. For the shot noise, it is usually have a formula on it, but for this lesson, it will be mainly focused more on the shot noise or the noise current for vacuum tube diodes. So we have a given equation here, which can be expressed as square root of 2 times B times I times Q, where I sub n is the noise current or the shot noise that is in terms of ampere, B is an equivalent noise bandwidth in hertz, I is the diode's DC current in amperes, and Q is the electron charge, or it is a constant that has a constant of 1.602 times 10 raised to negative 19 coulomb. And the final type of internal noise is thermal noise. Of internal noise is thermal noise. This noise is usually associated with the rapid and random movement of electrons within a conductor due to thermal agitation. This noise is temperature dependent because thermal agitation increases with the increase in temperature, and the vibrations produce thermal noise in electronic circuits. Most computations are usually under the thermal noise by the effect of the Boltzmann constant as entropy of the produced noise in the circuit. So we have the given equation here to express a power and voltage for noise in the given circuit. So we have the noise power can be expressed as P sub n is equal to KTP, where K is the Boltzmann constant, or is a constant of 1.38 times 10 raised to negative 23 joules per Kelvin. We have T, the absolute temperature, that it is in terms in Kelvin, and B is the noise bandwidth that is expressed in hertz. Noise voltage, on the other hand, can be described as square root of 4kTBR, where K is usually the Boltzmann constant, T the absolute temperature, B for the noise bandwidth, and R is usually the equivalent resistance of the given circuit. We need also to consider in thermal noise of these three in determining the total value on it. So we have the total noise voltage, which can be expressed as square root of V sub n1 squared plus Vn2 sub squared plus V sub n3 squared until to the voltage of n sub n squared. It is also same to the total noise current, which has similar to the noise voltage. However, the total noise power is just simply the addition of the noise power involved in the given circuit. So we need to also consider the noise system analysis. The first one that we need to consider is the signal to noise power ratio. It is usually a ratio of the signal power level to the noise power level and is used to determine the degree of intelligibility of a received signal of a certain system, which it can be expressed as S over N is equal to PS over Pn, where P sub N is a noise power in terms of watts and P sub S is a signal power in terms of watts. We can also express the signal to noise power ratio in terms of decibel, which can be expressed as 10 times log of PS over N, or just simply 10 log PS 10 log S over N in order to determine the signal to noise power ratio in terms of decibel. Another system that we need to consider is noise factor. It is the figure of merit used to indicate how much signal to noise ratio deteriorates as a signals pass through a circuit or series of circuits. So it is usually expressed as the ratio of the signal to noise ratio of an input device over the signal to noise ratio at the output device, which we can express of the given equation. Also, once we find the noise factor, we can also identify the noise figure, which can be described as 10 log F, where F is the noise factor and NF is the noise figure. So the next one is the equivalent bandwidth. It is a bandwidth of a perfect rectangular filter that allows the same amount of power to pass as the cumulative bandwidth of the channel selective filters. It is usually used in noise computations in reactive circuits. It can be expressed into B sub EQ is equal to pi over 2 times B sub 3 decibel, where B sub EQ is the effective bandwidth in terms of hertz, and B sub negative 3 dB or B sub 3 dB is equal to the half power bandwidth in terms of hertz. And we will also consider the equivalent noise temperature. This indicates the reduction in the signal to noise ratio as signal undergoes as it propagates through a receiver. It is a convenient parameter often used rather than noise figure in low noise, VHF, UHF, microwave, and satellite radio receivers. It can be expressed in this formula. We have T sub EQ is equal to T sub A times the quantity F minus 1, where F is our noise factor, where T sub A is the ambient temperature or the physical temperature of the circuit in terms of Kelvin, and we have the equivalent noise temperature referred to an input that can be expressed as T sub EQ in terms of Kelvin. So these four are the main systems of analysis on how we'll understand noise in electronic communications. So we need to also consider cascaded systems, where it involves it involves of block or amplifiers connected in a single circuit, which we can express as total gain of the cascaded system as G sub T is equal to G sub 1 times G sub 2 times G sub 3 until G sub N. However, if we can express in terms of decibel, it is just simply we need to add them up. So we have G sub T in terms of decibel is equal to G sub 1 in terms of decibel plus G sub 2 in terms of decibel until G sub N in terms of decibel. So if the given equation is not expressed in decibel, then most probably to compute for the total gain, we just simply multiply it. However, if the given if if the given values are in terms of decibel and we need to find the total gain, you just simply need to add. We will also consider in a cascaded system of these three, which refers to the noise factor, the noise temperature, and the noise resistance. So for the equivalent noise temperature referred to the input, each can be expressed as T sub EQ is equal to T sub EQ1 plus T sub EQ2 over G1 plus T EQ3 over G sub 1 times G sub 2. Overall system noise factor at the output, on the other hand, is also known as the Friis formula, which can be expressed as F sub T is equal to F sub 1 plus F sub 2 over R over G sub 1 plus F sub 3 minus 1 over G sub 1 times G sub 2. And for the overall system equivalent noise resistance, we can express in equivalent to R sub EQ is equal to R sub 1 plus R sub 2 over G sub 1 squared plus R sub 3 over G sub 1 squared times G sub 2 squared until R sub n over G sub 1 squared times G sub 2 squared times until G sub n minus 1 squared. So these four equations that we need to consider when you are calculating a cascaded system in determining the noise in an electronic communication circuit.